Okay, let's dive right into this explainer. Look around you for a second. Literally everything is made of elements, but to make sense of all of it, chemists don't just use some massive chaotic list. No, they have a map. The element map, navigating metals, nonmetals, and metalloid. Seriously, have you ever looked at the periodic table and wondered why it's shaped kind of like a distorted castle? Well, rather than just being some boring chart you had to memorize in high school, it's actually a highly organized spatial map. It's categorized into distinct territories. And, just like countries on a globe, each territory has its own specific culture and its own strict behavioral rules, based entirely on its atomic structure. As our source material perfectly points out, quote, "It is accurate to refer to the periodic table of elements as the symbol of chemistry," end quote. It's the ultimate key. This single symbol structures all known matter, guiding us through the chemical properties, reactions, and the raw potential of absolutely everything around us. So here is our travel itinerary for today. 1. The element map. 2. The mighty metals. 3. The non-metal territory. 4. The metalloid borderlands. 5. Trends in metallic character. And finally, 6. Why this classification matters. Let's kick things off with part 1, the element map, navigating the periodic table. Let's get the lay of the land, shall we? There are 3 major kingdoms that make up our 118 known elements: metals, nonmetals, and metalloids. Every single element you interact with falls into one of these big 3 categories. And these aren't just arbitrary labels either. They're anchored securely to specific locations on our map. Depending on where an element lives, we can instantly predict exactly how it's going to behave out in the wild. Which brings us to part 2, the mighty metals, the generous electron donors. We're starting our journey on the far left side of the map, exploring a vast, sprawling empire. So, what actually makes a metal, well, a metal? By definition, metals are elements that tend to lose electrons to form positive ions. Think of your classic heavy hitters, like iron, copper, and gold. The defining culture of this territory is, believe it or not, generosity. Metals naturally want to give away their valence electrons. You know, those electrons hanging out in their outermost shell, just to achieve a nice, stable configuration. Moving right along to part 3, the non-metal territory, the greedy electron acceptors. Let's travel all the way across our map to the far right side. What's super interesting here is the stark behavioral contrast. Non-metals are elements that tend to gain electrons to form negative ions. We're talking about elements like chlorine, sulfur, and phosphorus. So in total contrast to those generous metals we just talked about, non-metals are basically greedy by nature. They're actively hunting for and taking in electrons to complete their outermost shells. This brilliantly illustrates the ultimate chemical contrast. On the left side, we've got the metals losing electrons to form positive ions. On the right side, the nonmetals gaining electrons to form negative ions. This fundamental divide is literally the driving force behind so many of the chemical bonds and reactions that make our physical world possible. They are the absolute perfect chemical match for each other. Now for part 4, the metalloid borderlands, the dual nature elements. Now, elemental geography is rarely black and white. So what happens when these 2 opposing empires meet right in the middle? Well, they're separated by a literal stair-step borderland. It's a geographical border starting at Boron and extending down a zigzag path all the way to Polonium. The elements populating this specific border completely blur the lines between the 2 extremes we just discussed. These hybrid elements are known as metalloids or semi-metals. Some of the prominent ones include silicon, germanium, arsenic, antimony, and tellurium. They are absolutely fascinating because they can exhibit the properties of both metals and nonmetals. It totally depends on the conditions around them, like the temperature. Talk about a true dual nature, right? Up next is part 5, trends in metallic character, the invisible forces at play. To truly master this map, we need to uncover the hidden rules that dictate how these territories are formed. Which leads to a really great question. Why do elements lose their metallic edge as we move right across the table? Why isn't the whole thing just one big block of generous metals? Well, the answer lies in the atomic structure and a constant microscopic tug-of-war happening inside the atom itself. Let's break down the rules of this tug-of-war. As we read horizontally across a period, from left to right, metallic character decreases. Why? Because the core is getting more protons, which increases the nuclear charge. This stronger positive charge pulls those negative electrons tighter to the center, making it way harder for the atom to lose them. On the flip side, moving vertically down a group increases metallic character. Adding entire electron shells increases the atomic size, so those outer electrons get further and further away, and the inner layers actually shield them from the nucleus's pull. That makes them a whole lot easier to lose. And finally, part 6, why this classification matters, from table salt to digital devices. All this talk of atomic tug-of-wars is great, but how does this geography actually impact our lives? Let's look at the extremes. On the far left, we have highly reactive alkali metals, like sodium, which react vigorously with water. On the far right, we have the electron-hungry halogens. When these extreme opposites interact, the ultimate donor and the ultimate acceptor, they combine to create everyday salts. Yeah, literally the salt you sprinkle on your dinner. Meanwhile, the incredible electron-donating power of metals can be harnessed for pure energy. Take magnesium, for example. In powder form, it burns incredibly rapidly with an intense white flame. This highly energetic reaction is exactly what gives us life-saving SOS flares and those brilliant fireworks displays we all love. And hey, we definitely can't forget our borderlands. The device you are using to catch this explainer right now relies entirely on the unique dual nature properties of metalloids. Silicon is the metalloid semiconductor powering the entire digital age. It doesn't conduct perfectly like a metal, but it doesn't block completely like a non-metal either. This precise balance is exactly what allows microchips to process information. It's a real game changer. Which brings us to a final thought. If mastering the divide between metals and non-metals gave us the modern digital age, what undiscovered hybrid materials are waiting to be built next? As we continue exploring the endless combinations on this map, it really leaves you wondering what incredible new materials are just waiting around the corner. Thanks for joining me on this explainer. Keep exploring, and I'll catch you next time.